Empty space exerts measurable pressure. Two uncharged conductive plates placed nanometers apart in a perfect vacuum will move toward each other without any external force. This phenomenon is the Casimir effect. It is a macroscopic manifestation of quantum vacuum fluctuations and the boundaries they encounter in physical space. Between the plates, the electromagnetic field must satisfy specific boundary conditions. Only resonant modes with nodes at the plate surfaces can exist in this gap. Outside the plates, the electromagnetic field is unconstrained. An infinite spectrum of frequencies exists, creating a higher energy density than the restricted space between the plates. Every mode of the field contributes a zero-point energy equal to 1/2 times h bar times the angular frequency. Summing these leads to a divergence.
Calculating the total energy results in an infinite sum. In the simplest one-dimensional model, this sum is proportional to 1 plus 2 plus 3 plus 4 to infinity. To extract a physical force from this infinite energy, we must use rigorous methods from real analysis to regularize the divergent series. The Riemann zeta function is defined for complex numbers with a real part greater than 1 as the sum of 1 over n to the power of s. Through analytic continuation, we extend the domain of the zeta function to the entire complex plane, except for a pole at s equals 1. Evaluating the zeta function at s equals -1 corresponds formally to the sum of all natural numbers. The continued value is exactly -1/12.
This result does not mean the sum literally equals -1/12. Instead, it is the unique finite value associated with the series under analytic continuation. In physics, this -1/12 term is exactly what is needed to calculate the finite pressure difference between the plates. The resulting Casimir force is attractive. It depends on the Planck constant, the speed of light, and the inverse fourth power of the distance d. Because of the inverse fourth power relationship, the force grows exponentially as the plates move closer. Doubling the distance reduces the force by a factor of 16. At a separation of 10 nanometers, the Casimir effect generates pressure equivalent to 1 atmosphere. This is a significant mechanical force in microscale engineering.
In micro-electro-mechanical systems, or MEMS, this force causes moving parts to collapse and weld together, a failure mode known as stiction. Engineers combat stiction by using hydrophobic coatings or creating textured surfaces that minimize the effective contact area between components. Steve Lamorio first accurately measured the Casimir force in 1996 using a torsion pendulum and a spherical lens near a flat plate. Measuring two flat plates is difficult due to alignment issues. The sphere plate geometry simplifies the experiment and requires a proximity force approximation to calculate. Zeta regularization is one of many techniques. We can also use exponential cutoff functions or the heat kernel expansion to achieve the same physical result. A cutoff function suppresses high-frequency modes that are physically unrealistic, such as wavelengths smaller than the atomic spacing of the plates.
This process is part of renormalization. It involves subtracting the infinite energy of empty space to find the finite energy difference caused by the plates. Abel's summation treats a divergent series as the limit of a power series. For the sum of n, we evaluate the limit of n times x to the n. Cesaro's summation uses the limit of the arithmetic means of partial sums. While it fails for the sum of n, it works for Grandi's series. Borel's summation employs the Laplace transform of a related convergent series. It provides a powerful tool for summing highly divergent asymptotic expansions in physics. Leonhard Euler was among the first to explore these sums. He used functional equations to propose that 1 plus 2 plus 3 equals -1/12.
Modern real analysis provides the epsilon-delta framework and complex analysis required to make these early intuitive leaps mathematically sound and reproducible. The Casimir force depends on the dielectric properties of the materials. Real metals are not perfect conductors and allow high-frequency fields to penetrate. Lifshitz theory generalizes the Casimir effect to include temperature and arbitrary material properties, using the fluctuation dissipation theorem of statistical mechanics. By choosing specific materials and fluids, it is possible to create a repulsive Casimir force, causing objects to levitate at the nanoscale. The vacuum energy calculated in the Casimir effect
is a candidate for the cosmological constant, which drives the accelerated expansion of the universe. The predicted vacuum energy density from quantum theory is 120 orders of magnitude larger than observed, the worst prediction in physics history.
Calculations of the Casimir force often involve the fine structure constant alpha, which characterizes the strength of the electromagnetic interaction between particles. At room temperature, thermal fluctuations contribute to the total force. At large distances, these thermal effects dominate over the quantum zero-point energy. The Casimir polar force is a related effect between a single atom and a surface, caused by the interaction of the atom's fluctuating dipole moment. Mastering the Casimir effect is essential for the next generation of nanomachines, allowing for frictionless bearings and ultra-sensitive force sensors. The Casimir effect proves that divergent series are not merely mathematical curiosities. They are essential tools for describing the underlying structure of our universe. We have seen how analytic continuation transforms a divergent sum into a precise physical prediction, bridging the gap between real analysis and quantum reality.
The negative 1/12 result is confirmed by the force that holds these plates together, proving that nature follows the rules of regularized sums.